Hey, I'm Eric, and this is my AlphaXiv and Marimo entry, a paper by Li and He called Back to Basics, or JIT. Now, every diffusion model is trained to predict noise. JIT says, however, predict the clean image instead. That ought to be harder, but it's actually easier for a surprising reason, which is what this notebook is about. And along the way, I try to test something that the paper doesn't. So here's the picture. Real images, and I'm using the CIFAR-10 dataset, don't fill their pixel space. They sit on a thin, low-dimensional manifold surface inside of it. And so the clean image stays on that surface while the noise, which we generate during training, fills the space around it, which means predicting the clean image is a much smaller problem than predicting the noise. That one difference is the entire JIT bet. So you don't need equations to feel this concept and build a widget using my agents. So drag anywhere. Each spot is a noisy image. The indigo clean image always snaps to that one-dimensional curve, while the amber noise dots scatter everywhere. If you scroll down and hit the measure dimension, the clean data points are approximately one-dimensional, while the noise is approximately two. So you found the paper's argument just by playing around. So let's say why. The math is one line. Noisy images equals clean images plus scaled noise. The only choice here is what the network predicts, the noise across every dimension or the clean image back on the manifold. Bigger patches means more dimensions, so that gap becomes a cliff, which is why JIT uses big patches on purpose. So does predicting the noise actually break? I measured it on the GPU. Same network, same toy data, only the target differs, and predicting noise just collapses. By 3,000 dimensions, it's no better than guessing the average. The clean image does the opposite. It keeps getting better, and that's the game's picture, now with numbers. So that made me build the real thing using the CIFAR dataset as raw pixels on the GPU, no tokenizer, no VAE, just fed to a diffusion transformer of about 7 million parameters, written from scratch in the Marimo notebook. Then I trained it on a Blackwell GPU. Honest about scale, this is a sketch, not a paper's 600 epoch run across 8 H200, but it is a real pixel transformer, enough to put the idea to work. So that's the training curve. And so then does it actually generate? From pure noise, each class finds its own color and texture. But honestly, if you look at this set of images here at this scale, you get colored patches, not like real cars and horses. Real objects are the paper's regime, way beyond this notebook. But this is just to test the idea, so the quality's deliberately small. And that made me a little curious. The whole argument assumes images sit on a low-dimensional manifold, but the paper doesn't really check that. So I decided, let's check that. We did a PCA over thousands of CIFAR images, and it shows that 95% of the variance lie in just 208 of 3,000 dimensions. And it's real, and it's thin. So if it's real, the model ought to be able to find it, which is to be able to project the noisy input back onto the surface, which is basically what denoising is. And I used it as a denoiser, which is to corrupt an unseen image and then do one forward pass. And this chart shows up to 22 decibels of improvement, beating a blur at every noise level. So for example, if I were to very briefly drag around, I need to get out of this mode. If I were to drag around the sigma over here, each row, by the way, is clean, followed by noisy, followed by recovered, all in one pass. And as I increase the amount of noise, you can see that our trained model can behave somewhat like a denoising model itself. Of course, the quality isn't the best, just because this is a small model. But this is the punchline. Denoising and generation are the same operation, both just projections onto the manifold. So one idea runs through the whole thing, which is to predict the clean image. And this works because denoising means finding the manifold. And that game above makes it a little bit tactile. We did a bit of sweep to understand the idea better. And the model we showed does do that as well. I built this live in Marimo with the Marimo pair skill on a MoLab GPU. It was pretty fun. Thank you.